In this case, it is volume. And the only reason why I chose H there is that I already have a D here, so I didn't want two Ds. Normally we take D as the separation between plates. And so this now is another way of looking at electrostatic potential energy. We look at it now only from the point of view of all the energy being in the electric field, and we no longer think of it perhaps as the work that you have done to assemble these charges. I will demonstrate later today that as I separate the two plates from these charged planes, that indeed I have to do work. I will convince you that by creating electric field, that indeed I will be doing work. So from now on, we have the choice. If you want to calculate what the electrostatic potential energy is, you either calculate the work that you have to do to bring all these charges in place, or if it is easier, you can take the electric field everywhere in space, if you know that, and do an integration over all space. We could do that, for instance, for these two parallel plates now, and we can ask what is now the total energy in these plates, in the field. And at home, I would advise you to do that the way that is done in your book, whereby you actually assemble the charges minus Q at the bottom and plus Q at the top, and you calculate how much work you have to do. That's one approach. I will now choose the other approach, and that is by simply saying that the total energy in the field of these plane parallel plates is the integral of 1/2 epsilon 0 E squared over the entire volume of these two plates. And since the electric field is outside zero everywhere, it's a very easy integral. Because I know the volume that I have, if the separation is H, so we still have them H apart, this volume that I have is simply A times H, and the electric field is constant, and so I get here that this is 1/2 epsilon 0. For E, if I want to, I can write sigma divided by epsilon 0. I can square that, and dV, in doing the integral over all space, means simply I get A times H. It is the volume of that box, so I get A times H. And so this is now the total energy that I have. I lose one epsilon here. I have an epsilon 0 squared and I have an epsilon. I also remember that the charge Q on the plate is A times sigma, and that the potential difference V, this now is not volume, it's the potential difference between the plates, is the electric field times H. The electric field is constant. If I go from one plate to the other, the integral E dot dl in going from one plate to the other gives me the potential difference. And so I can substitute that now in here. I can take for A sigma, I can put in the Q, and you can also show that this is 1/2 QV. V being now the potential difference between the plates. And so this is a rather fast way that you can calculate what the total energy is